Hi everyone. So we'll start this Generative AI 101 series with the introduction to large language models. In this video, we'll understand what the neural networks are and how they are related to large language models. We'll try to decode the language modeling problem which these large language models are trying to solve. We'll demystify the model training process, see the LLM landscape where all these companies like Nvidia, Hugging Face, OpenAI are coming in, and then redefine the language modeling problem at its core. Then when we will look at the next token prediction task, what these language models solve and how it contributes in the emerging abilities of the large language models. And then we look at the scaling laws and some potential evidences of their plateaus. First of all, thank you so much guys for showing so much love and support for the first video in this series. I'll make sure I try to provide as much content of the premium quality for free for as long as I can. So let's start with the introduction to neural networks. We'll start with the very basic definitions, and by the end of this series you will have an even much deeper understanding. So let's start off with the very simple definitions first. So all I can say is it's a kind of a machine learning model, or we will simply call it as a model. And these models are kind of black box systems. When we say that, oh, there is this trained neural network, think of it as a simple black box system. What a black box system is, it takes some input and it generates some output. Simple. How it does that, we don't need to know about it. It just takes some input and generates the output. And there are some neural network architectures you might be knowing, or you read about them in the news or anywhere else. For example, this is called a feed-forward neural network. It takes some input and generates the output. This is all you need to learn. Again, there's this another one which they call it convolutional neural network. It takes an image as an input and generates some output. So these are the kind of neural networks which work with, let's say, images. And there's this another neural network which works on like sequential data. They call it LSTM or RNNs. This is also another kind of an architecture. The one which is quite famous nowadays is they call it transformer. But the core of all these models is once these are trained, they are like different images of one black box. They take some input and generate the output once they are trained. The training process is quite complicated. We'll discuss that later. But the whole idea of neural networks are they are black boxes. Once they are trained, you give them the input, they can generate the output. So to simplify this discussion, all I can say is this model, think of it as a neural network. It takes this input and it will generate the output. This is how you should think about neural networks. And then let's look at the example to make this idea very much concrete in our mind. For example, in the case of agriculture, the input could be the crop leaves, and the prediction that model makes, the output it generates is whether the crop is healthy or it has some disease. In finance, it could be you can give the historical transaction as an input, and the output should be whether it's a fraudulent activity or not. And hedge fund manager can give the features of the stock as an input, and the model predicts whether to buy the stock or not. The real estate, you can give the features of house as an input, and the model will predict whether what's the price of this house. In healthcare, you can give the patient's data as an input and generate whether model will predict some kind of diagnostics or say the likelihood of any disease. In e-commerce, it could be a recommendation based on the purchase history of user as an input, and it generates the output. And in human resources, you can give the resume and all the job applications that has come and find which candidates are good or not, right? And in energy case, energy consumption, what we can do is we can give the historical consumption of the data in any society anywhere and predict the future demand based on the time of the year and all those things, right? And in education, you can give the student's performance as an input and see, okay, which are the topics he might be struggling with, and the concept of like whether he'll drop out of this class or not, right? And these, if you look at the core of all of these examples, all it means is once the model is trained, it can do all these things. If we have a simple definition of these neural network architectures, you give it an input, it generates the output. The way the magic is being done will be decoded in these videos, but at this point, the whole idea I'm trying to communicate is that the neural network, once it gets trained, it can does this kind of magic, and all you need to do is you need to figure out what the input is and what the output is. Let's try to formulate our understanding for large language model based on our previous definition of model. All we can say are they are like now these big large models, right? So large language models, how could we define it? They are large models, large black box systems which work with language. Pretty much the simplest definition we can come up with for large language models. So now let's see what it means. More specifically, I can say that they are like those big sophisticated neural networks which are trying to solve the language modeling task. The language modeling task we'll define later, but at this point, all we need to understand is these large language models, they are some kind of sophisticated neural networks, right? And this is how they look like. The image you see, the input is a language and it generates certain language as an output. And this particular architecture, we'll call it large language model. It takes language as an input and it generates language as an output. So if I redefine or like simplify the LLM now, all we can say is it takes some kind of a text as an input, it generates some kind of text as an output, and this is also again a black box, a trained black boxed large language model which does that for us, right? So for example, now we'll look at some of the examples. For example, for the customer service, we can give the input as a customer query and LLM generates some relevant answers. For legal documents, it can summarize those documents if we supply them as an input. In healthcare, we can give the patient's medical history, all those as an input, as a text, and it generates the output. And in finance, we can give the financial reports as an input, and the LLM generates the company's financial health output, like or what kind of reports that you want. And in education, we can give the user's question, like we also use ChatGPT to ask this question, and this LLM can answer those questions. And in human resources, you can supply these job descriptions, resume, and LLM gives the personalized messages to reach out to those candidates. In content creation, we can do that. Like basically, we supply the marketing content, product descriptions, and everything, and it generates those social media posts, all those things. And in real estate, we can give the details of the property and it can draft a proper description of that property, a listing they call it. And in retail, we can give the shopping history and everything for the user, and the personalized recommendation emails it can send out directly to the customers. And in non-profits, we can get the donor's history and the campaign goals he has, and we can send him the personalized outreach messages using these large language models for fundraising assistance. Let's define this language modeling task. What exactly this task, what exactly this problem is. So the problem definition of language modeling is that we try to predict the probability of the next word that can come in the sequence of previous words. Just to simplify it, we can say that if any model who has solved this language modeling task, it can tell the probability of a quick brown fox jumps is higher than a jumps quick fox brown, which means that if there is if a model who has solved this problem of language modeling, it can predict which sequence of tokens, which sequence of, for example, these words form a decent sentence. The probability of a good sentence becomes higher according to that model. So the language models are just trying to solve this problem of understanding which is the probable sentence or which is the most probable sequence of words based on the words that we give as an input. So there are two techniques to solve this problem. Another one is the statistical counting method. It is like you just count the frequency of certain words in the presence of other words and try to formulate probability on top of that. Another approach is neural network based approach, where we train a particular neural network architecture to generate the next word as an output when we supply certain words as an input. So basically, if you remember, the neural network was we give it as an input and it generates some output. So if to a neural network we give certain words, that the input words, and ask it to generate what could be the next word, that becomes a next token prediction task for a neural network. And if a neural network can solve this task, it becomes a language model. Just to keep a simplified visual representation, think of it as a neural network to which we give an input, cat sat on a, and if it can generate that, look, next word could be mat because cat sat on a mat with the probability 97%. It means this model has learned that if the input is cat sat on a, I can generate the next highly probable token. They call it next token prediction. If it has solved it, it will say mat. You can use any architecture. For example, if you use this one architecture, now they are called large language model, some variant of this. So this neural network becomes a language model if it solves the task of next token prediction. So if we simplify it even more, what we can say is language modeling, the models which are solving this language modeling task are called language models, and these language models can be known as text completion engines because you give it some text and it just try to complete it. Think of it as fill in the blanks, right? So the moment you give certain text as an input, it try to fill it up with the next upcoming tokens based on the input that you have given. So let's demystify the process of building these black box models. First step we have to decide is what is the architecture that we plan to train. For example, let's pick this architecture called transformers, right? The next step is we say, okay, let's look at the data set. For example, in this use case, let's pick up all the Upwork reviews any client has given to any freelancers, right? Let's say we prepare the data set. What we do is then we create a training objective for our task. For example, if we are building these language model, you can say, okay, the next token prediction sounds good for us. So for example, this is one of the reviews that one of the clients have written for me for chatbot development. So what we can do is we can pick certain sentences out of this review and create this next token prediction. For example, there are some kind words that my client has used. For example, Sanjeev is the most talented person. I pick this sentence, I give the input as Sanjeev is the most talented hyphen, like the blank, what could be the next word. The actual output is person, and then you cannot go hiring this man for machine learning project. So again, you cannot go wrong hiring this dash, and the output is man. So what you do is you create this supervised data where you tell the neural net, this architecture, that hey man, this is the input and this is the output also, based on the data that we have. Now this kind of pairs of input outputs is this architecture gonna use, and it's gonna train itself to make the predictions whenever a certain input comes to predict the next probable word. How it does it even more detail is the purpose of this playlist. But at this point, we are intentionally creating these pairs out of this data set, and we will feed these input output pairs to our particular architecture in the process of building these black box models. So now, if I simplify what happens in the process of training is, we have this data set, let's say all the reviews from different clients to different freelancers, we collected that. We decided this particular untrained architecture, let's say it's not trained yet, but we have decided the architecture. This is the architecture we're gonna use, the transformer. We put this architecture and this data set on our GPU servers, compute servers they call it, and ask the model to train itself based on this data. And after a lot of iterations of trial and errors, the model trains itself and something comes out of it. This process, we call it parameters. So these parameters are certain numbers that gets fed into this architecture, and this architecture becomes a trained architecture now. So there were some gaps, there were some numbers that this architecture was looking into. After this process for days or months of trainings, this parameters file come out. We can fill these parameters in this architecture, and now it's called a trained black box system. All it has done is it has memorized this data set as world knowledge inside it. The way we call it is, it's a compression process, and this is a knowledge which gets compressed in form of parameters. And now let's look at the LLM landscape, and all the companies, what in this process of building these neural network architectures and the training of these processes, where all the companies fall into place. So there's this AI hardware manufacturers, companies like Nvidia, which are supplying GPUs. There are these AI cloud platforms, which they say is will give you the servers also with GPUs and all the configuration setup, AWS, Google Cloud, and Azure, etc. These companies are providing the cloud services for you to train and host the trained models. And then there are these open source modeling companies which host a bunch of models like Hugging Face and all. If somebody trains a model, they upload it there, and you can download it on your machine or on your servers and use them for free. And there's this LLM access via API. In these companies, they train the model. They say we can't give you the weights, the parameters and everything, but you can access the trained model via API. You might have used ChatGPT API, Anthropic and other companies. What they supply you is an API based access to those models. You don't get to know the weights, the architecture, nothing. They say we'll keep it hidden to us, but we'll give you access based on certain price per call. And then there are these customer facing products, like once they build the LLM based models and all, and then they supply you as a client based interface, things like ChatGPT, Gemini or Meta AI. They give you an interaction based system here. So now let's look at the core of LLMs. So basically LLMs are just a parameters file, and there's this run.c script which runs those parameters along with the input you supply to generate an output. Just an example from Meta. Meta released this Llama 3.2 model with different versions, 1B, 3B, 11B or 90B. All of these are different sizes of like 1 billion, 3 billion, 11 billion or 90 billion is the size of parameters file. Basically this is a parameter.zip file in various sizes, Along with, there will be some kind of a file which runs those parameters in that particular architecture along with your input. This is just loads the model of that particular architecture, and this knowledge is used to convert input to output. So in a nutshell, this is what LLM is: a simple parameters file and the way to run those parameters. That's it. This is like the core slide that you should keep with yourself whenever somebody asks you what exactly is an LLM. So now I want to discuss this idea that why just this fill in the blanks problem statement, or like this next token prediction task, is so powerful. So what happens is, imagine this is my Upwork's profile page where I'm talking about what I work on, what I have done in the past, and what is my expertise. If we put some of the fill in the blanks from here, like, oh, I have worked at Google at a planet scale data, or worked in companies like Amazon and LinkedIn. I didn't mention anywhere that what Amazon does, what LinkedIn does, or anything like that. But based on this itself, the machine can, if machine learns to fill that information, that, oh, the moment as I am a specialist in machine learning and deep learning, things like that, this architecture will get to know that, oh, Google, Amazon and LinkedIn, like these companies, also work in the space of, let's say, fraud detection, demand forecasting, conversion optimizations, or machine learning based projects. So this, if the model has to become good at this fill in the blanks problem statement, it has to know a lot about the world. That's why this next token prediction task, it looks so simple, but still gets a lot of knowledge of the world in the process of doing that. Just let's do a case study about it. In OpenAI, this is just a major theme. So what OpenAI did is, they said, okay, let's select a particular transformer variant. They chose the decoder part of the transformer in their certain way. They made some changes and all, which is not known to anybody in public. And then what they say is, let's download a chunk of internet. We don't know which part of the internet they downloaded, but let's say they downloaded Wikipedia or anything like that. And what they said is, we will do this next token prediction task. That's all they did. And if you want to take one lesson away from this study, all it says is, focus on the simplest problem, scale it massively, and use the existing technologies, and you can build $1 billion enterprise. All they did is this simple next token prediction task at scale. Once they solved that problem, tried many things like fine tuning and all those things on top of it, by RLHF, all those things like that, and then you can build a product like ChatGPT. Now I want to talk about this idea of scaling laws, that why, like, this skill, there's this Intel's paper on the power of scaling and in the large language models term. So basically all it says is bigger is often better, and large model and more data is always going to give better results. Of course, you have the compute as well. So basically it's a idea of, like, having a balance between the number of parameters and the number of tokens you're planning to train this model on. Basically it says that the performance of large language model is a function of the size of your model, the parameters file, and the dataset that you use. The more the dataset size, the more the number of parameters in your model, the better this model is going to be. Basically you get this intelligence for free just by scaling. So the more compute you have, the more dataset you have, the more the number of parameters, you will have a better model. Of course you have to have various innovative ideas also, but in general, like, this will give you a better performance compared to other models. And now, but this is a problem. Recently there's been this debate about, like, even this amazing person on internet, LeCun, he keeps telling that, like, the token prediction task is not enough on its own. Even the baby, he's not learning about the world just by, like, next token prediction. He just looks at the world very simply. He's observing by his eyes and see a lot of things and learns a lot about just with visual interpretation, right? So this Elias Witzbaker, co-founder of AI Labs, he also, and also OpenAI, he also mentioned that, like, scaling laws are now trying to plateau. And LeCun was saying it for a long time. There's this funny meme nowadays on internet. I don't want to say I told you so, but I told you so. Yeah, he was saying this so long that, like, large language models are not enough to build AGI, and the co-founder of OpenAI is also agreeing to this. So now there might be a new wave of innovation if people gets to realize that, oh, LLMs are not enough, maybe we have to come up with different architectures and all. And yeah, this is good for everyone. So yeah, in next video we'll try to cover the limitations of large language models and try to enhance the models using rags, prompting, and prompt engineering and fine tuning, and then we deep dive into transformer architectures also, and then we'll talk about AI agents as well in the coming videos. So meanwhile, guys, like this video, comment your questions, or help someone else who have asked some questions, and share this video with your friends who can benefit from this video, and also subscribe to this channel. Thank you so much for watching, guys. Bye.